Hello, welcome to my final project for AVI450 Aerodynamics. And in this project, we make this Gillows glider fly backwards the way it's not supposed to, with a canard design. Please excuse the mess of several other airplane projects, such as this glider wing and this flying wing aircraft. And this possibly quite broken quadcopter here. The first task was finding the mean aerodynamic center of the horizontal stabilizer and the 25% aerodynamic center on the wing. So we have that marked here. And as you can see, I did the angular calculation here for finding the mean aerodynamic center and then found the 25% mark right there. Right here we have the calculations for the area, and that leads into the calculations for the lift of the horizontal stabilizer, where we have the various dimensions for this not normal hexagon. I suppose irregular hexagon is the proper terminology. The horizontal stabilizer has an area of 0.03201 square feet. And the main wing has an area of approximately 0.1666 square feet, and that's assuming it's a perfect rectangle, which of course it's not. There's a slightly rounded corner, but we assume it's a perfect rectangle for simplicity's sake. Right here are the calculations for the lift produced by the wings total by adding together their surface area. So as you can see, the total lift is going to be 0.004721, and I believe that is in pounds per square foot. And assembling as the glider as it is intended to be assembled, we can see that the mean aerodynamic center is going to be forward of where the CG is, which should mean that the wing will be producing lift forward of the CG, therefore causing a pitch moment upwards. A quick flight test demonstrates that it does indeed pitch up and then stall and descend again. This leads to an oscillation where it stalls and falls again. It is unstable due to the center of pressure being forward of the center of gravity. Now, by sliding the wing to the rear, you can see it actually moves the center of pressure back behind the center of gravity. So here we have CG1 marked as the center of gravity when the wing is in the forward position. And of course, moving the wing back moves the center of gravity back due to the weight of the wing. But now you can see the center of gravity is slightly forward of the aerodynamic center point where the center of pressure is. Having the center of pressure behind the center of gravity will create a stable situation, as the tail has a negative angle of attack and will counter that pitching down motion caused by having this weight at the front with the center of gravity in front of the center of pressure. And with a test flight, we can see that now, with the wing in the rear position, it flies in a stable fashion and will just keep going straight until, that is, it hits something. Now I'm going to rebuild the glider like in this picture, where we take the wing out. It will be flipped around. The pilot is going to go in the back. The whole fuselage is going to get switched around. I'm going to put the horizontal stabilizer flying first. We're going to put the wing in the rear position, which used to be the front position. That's now the rear position. The vertical stabilizer will go where the pilot was, just like so. And the pilot is going to go right up here. Man, let's hope he doesn't crash. That would be a bad day. So as we can see now, the center of gravity will have obviously moved, without this weight, that is. The center of gravity should now be right here, just forward of the wing. And we actually can calculate that. Here I measured the distance between the front canard center of pressure and the rear wing center of pressure, and it was 3.75 inches. And that is a ratio of 5.2 to 1 for the center of pressure, the lift produced by the canard, and the lift produced by the wing, which means for every 1 unit that the center of gravity is away from the main wing center of pressure, it should be 5.2 units from the center of pressure of the canard. And that ended up being about 3.145, which for this 3 1/8 inches worked fine. 3.125, that worked out fine. And then it was 0.6048 inches from the wing. So you can see we have the center of pressure for the wing is right here, and the canard center of pressure is right here, and 3.125 inches from there is where our center of gravity should be. So we need to relocate the weight to where our center of gravity ends up right there. And it just so happened to be that that weight, in order to create that moment where we need it to be, should be right here. So let's go give this a flight test now. And so, with the pilot in his new precarious forward position, it will glide as long as it does not hit any support beams. Let's try that again. Man, it really likes curving towards the stove here. There's probably a thermodynamic reason for that. And third try is the charm. Here we go. Whee! There it goes. One more for good measure. It does indeed glide. So as you can see, you need the weight pretty far forwards now to counteract the positive lift here by the canard, as opposed to before, you needed it very far at the front to oppose the downward lift of the horizontal stabilizer, because you can see it is at a negative pitch relative to the main wing. That is why normally aircraft can fly faster and be more efficient when they are slightly tail heavy, because like with large airliners, having the extra weight in the back means they don't have to use the elevator as much at a negative pitch to keep the nose up. Instead, they can have that weight do that, which means there is less aerodynamic drag induced by the negative lift of the horizontal stabilizer. That's just an extra little detail, but that should cover everything for my final project.